All right, program demonstration for the hash table operation performance measurements. Just get right into the code here. JSON files that were created with really generic names and then randomly selected states from within the United States. And so there's 10 entries, 100 entries, 1,000 entries. They're called 1,000 entries realistic because the first time I had these generated for me for a data set, they were unintelligible names. So I had to get a little more specific, and it helped me get those. But for the main program, pretty straightforward. We've got the hash table. Run a JSON, time, and CSV for our import libraries. JSON to read the files, time to measure performance, and CSV to format the output of the performance data. Hash table initialized with buckets of entries, so whatever entries those are, they're considered buckets, just kind of contains all the stuff per entry. Since it's not always just a key value pair, the hash function just returns the hash key. The insert method here just pops the key value pair into the hash table. And then we've got the retrieve method to retrieve a value. And then I've got print table, which originally was on its own, but I have these three separate functions because if I want to output this 1,000 element hash table, then I have to do it alone. I have to do it by itself because it's such a large output. It really doesn't fit in the console. So I don't really run that one. I just have the function for it. I tried it with 1,000. You can do it, but it's just not even worth scrolling through all of it. This function just loads the data set from the JSON file right there. Load. Measuring runtime. This is just a function that takes a function and its arguments so that you can basically wrap the function that you're running in this one, which measures the runtime with this performance counter. And so it starts it and then runs the function, saves the result, and then ends the performance counter and then calculates the difference between the two and returns that as um, the performance time, the time. I can't remember what it's down here. You can see it, but this one's for the measuring for the sort. So I just ran the normal sort. I could run a more complex algorithm, but with a hash table, it's not really necessary. It's kind of the point of them, which is nice. Yeah, sort time. That's the one that comes out of that measure runtime one there. Sort time comes out of that, and then it shows it in the console, returns it. Saving performance data, just check if the file exists. If it doesn't, try to open it. And basically, formatting the data here is just for the CSV sort of style. And then this right here is the file writer for it. So it just writes it in the row. Insert time, sort time, data set size. Very simple, 3 numbers. Here we have the data sets get loaded from their relative paths. Create and populate the hash tables. Let's create them here, and then the population of it happens here, but the insert times, these anonymous variables right here basically mean nothing. These are throwaway variables, that's why they have no name. They're just underscores. But the insert time 10 comes out of the measure runtime for the lambda hash table 10 dot inserts. You're calling the insert method from the hash table data structure, and you're just for each one you're just f stringing in these entries for each one. Just put it all the way through into this hash table, and then obviously the insert time is stored right here, or is stored here and then displayed there. Same thing runs for the 100 and the 1,000. Measuring the sorting time, I just store this right here since it's not a so the measure sort runtime is only different from the insert time just because of the fact that it's wrapped a little more, just because the sorting has its difference in its function, right? So the sorting function has to go through all the entries and do a lot more work than just the insert one, and the measure sort runtime is not a class method, and the insert one is. So insert is a class method, so you get to call it directly from the object. This one here, it doesn't work that way. You have to call it separately. So here I've got these. The ones can be uncommented for debugging, so you can just print it out if you want. Collecting the performance data, and then save the performance data to the text file. Text file's right here. You see at the top we got insert time, sort time, data set size, and it saves them all. They barely fluctuate. Right now it's at 34 lines. If I run this, it'll give us the sorted list down here. So this just shows that it does sort it. Saves, shows the times, and then you got, 5 barbers with different last names. And there have been doubles, or so-called collisions, in the 1,000 entry dataset, and it handled it just fine. And now the performance data goes to line 37, so we added 3 lines to that. Now once the data's in this here, I go over this get time script, and this is one that from data analysis and statistics, I've gotten really comfortable with this kind of code and kind of pulling it into a data frame, reading a CSV from a text file or from a direct CSV file if it's that format. I have to convert the columns to numeric values. When they're saved in TXT, they're strings. You just group it by the data set size and then find the average of the insert time and the sort time and set up the plot. Mark the x-axis for the different sizes, 10, 100, and 1,000. Add a position mapping, because if you tell it you want 10, 100, and 1,000, it'll think that 1,000 is like the maximum value of the x-axis, when this isn't really going to be plotting from left to right. It's a bar graph, so it doesn't matter if they're spaced out correctly on the x. It's more about the data set sizes showing different data or different performance metrics. Plotting everything and setting up the title and everything like that, and then displaying the value above each of the bars, display the plot. I've got a copy of one of these in the Word document or Google Docs that is saved in the file as well. So insert time with its values, sort time with its values. You can see the insert time is following probably an O of n squared, and the sort time is following like an O of n, maybe it might be just like an O of n, I don't know, between 100 and 1,000. It kind of gets 10 times bigger. So this one seems like O of n log n, maybe like pretty linear. If you understand that it's, this one's 10 times larger than this one, so it's not like it's going up evenly. It's a little bit deceptive of a graph there, but this one, it's about 10 times bigger too. So it's probably pretty linear. Seems like it's a pretty straightforward thing, and I know that hash mapping is one of the most efficient ways to organize data. So I know it's typically found to be linear or near that, and that's all.